And welcome back, students. As we jump into our next lesson on recursion, let's take a closer look at recursion today so we can expand upon what we learned last time. So, getting started. The definition of right vertical, if you recall, uses recursion. Yet, when we looked at that definition, we did nothing new or different in evaluating the method call for right vertical 1, 2, 3. We treated it just like any of the method calls we saw in previous units. We simply substituted the argument 1, 2, 3 for the parameter n and then executed the code in the body of the method definition. When we reached the recursive call, right vertical 1, 2, 3 divide by 10, we simply repeated this process one more time. So, how recursion works and how it ends. The Java language places no restrictions on how recursive calls are used within method definitions. However, in order for a recursive method to really kind of be useful, it must be designed so that any call of the method must ultimately terminate with some piece of code that does not depend upon recursion. Otherwise, it's going to keep calling itself. Now, the method may call itself, and that recursive call may call the method again, as we witnessed with our method that we saw last time. It's like, hey, met the condition, call the method. Hey, I met the condition still, call the method. And theoretically, as long as it meets that condition, it can keep calling it. This process can be repeated any number of times. There's not necessarily a set limit of saying, oh, recursion can only go for 5 times, or it can only go for 10 times. No, it can go as many times as you need it to go in the instance of your program. However, the process will not terminate unless eventually one of the recursive calls does not depend upon recursion to return a value. That's why we had the if-else statement in there, because we needed some way to terminate that recursion. So when we look at recursion, there's 2 things to kind of look at, base case and stopping case. The general outline of successive recursive definition is as follows. One or more of the cases in which the method definition accomplishes a task by using recursive calls to accomplish one or more smaller tasks. One or more of the cases in which the method definition accomplishes tasks without the use of any recursive calls. Remember before we had the simple case and then we had the recursive case. The simple case was just the if and it tested it, just did a print statement, and then the else, which was the recursive case, that did the recursion call. Now, these cases without any recursive calls are called base cases, or otherwise known as a stopping case, because that's what gets the recursion to stop. So, often when we're looking at recursion, an if-else statement is determining which of the cases is going to be executed. So, nothing really kind of new here. We see this in our example. We are very familiar with using if-elses, so this is something that we can handle fairly easily. A typical scenario is for the original method to call execute of a case that includes a recursive call. That recursive call may in turn execute a case which requires another recursive call. For some number of times, each recursive call produces another recursive call, but eventually, one of the stopping cases should apply. All right, as we saw last time, when we looked at our example, it was when n was less than 10, and so once we got down to calling with the parameter value 1, well, 1 is less than 10, therefore call the stopping case. Now, every call of the method must lead eventually to a stopping case, or else the method call will never end, and will cause an infinite chain of recursive calls. It's just going to keep calling recursion over and over and over and over, pretty much until your computer runs out of memory. Now, in practice, a call that includes an infinite chain of recursive calls will eventually terminate abnormally rather than actually running forever. You do have a finite amount of computer memory, so keep that in mind. Now, the most common way to ensure a stopping case is eventually reached is to write the method so that some positive numeric quantity is increased on each recursive call and to provide a stopping case for some small value. That's how we designed our method right vertical. We checked it with n is less than 10. Now, with the method right vertical, when we call that, the call produces a recursive call with a smaller argument. Because remember, I started, like, for example, we did 1, 2, 3, 4. The next time we 1, 2, 3, then 12, and then just 1. This continues with each recursive call producing another recursive call until the argument is less than 10. When the argument is less than 10, the method call ends without producing any more recursive calls, and the process works its way back to the original call, and the process ends. Alright, let's discuss quickly the general form of recursive method definition. The general outline of a successful recursive method definition then is as follows. One or more cases that include the recursive calls being defined. These recursive calls should solve a smaller version of the task performed by the method being defined. one or more cases that include no recursive calls. And these cases without recursive calls are called base cases or stop cases. Now note, you'll see it says one or more. So you can technically have like an if, an else if, an else, and maybe your else is the recursive call, and your if and your else if are other scenarios of things that you want to happen. Alright, so we've been alluding to this, kind of mentioning it, but here's that pitfall for recursion, which is infinite recursion. In the example of the method right vertical discussed in the previous subsections, the series of recursive calls eventually stops when these reasons call the method that involve recursion, that is, a stopping case. If, on the other hand, every recursive call produces another recursive call, then a call to the method will, in theory, run forever. This is what's known as infinite recursion. In practice, such a method will typically run until your computer runs out of resources, as I've already mentioned, and the program will terminate abnormally. Now, examples of infinite recursion aren't hard to come by. So think about our right vertical. If we had changed that from n is less than 10, for example, to a value that we would never reach. So, if it's always, let's say it went, 1, 2, 3, 4. Let's say n is greater than, we had input, let's say 1, 2, 3. If we say we put n is going to be greater than 1, 2, 3, and our input is 1, 2, 3. Well, technically 1, 2, 3 is not true for that statement, so it's going to always fall into the else. So the following is a syntactically correct Java method definition, which would result from an attempt to find an alternate version of the method right vertical. So here I have public static void, new right vertical, and new right vertical, and divided by 10, system of print line, and mod 10. Now, if you embed this definition in a program that calls this method, the program will compile with no error messages, and you can run the program. Moreover, the definition even has some certain reasonableness. So you look at the code, everything so far looks like it could make sense. It says that to output the argument to new right vertical, first output all but the last digit, and then output the last digit. However, when called, this method will produce an infinite sequence of recursive calls. If you call, for example, new right vertical 12, that execution will stop to execute the recursive call, new right vertical 12 divided by 10, which is equivalent to new right vertical 1. The execution of that recursive call will, in turn, stop to execute the recursive call, new right vertical 1 divided by 10, which is equivalent to new right vertical 0. This, in turn, will stop to execute the recursive call, new right vertical 0 divided by 10, which is equivalent to new right vertical 0. This will produce a recursive call again to execute the same recursive method call, new right vertical 0, and so on forever. Now, because the definition of new right vertical has no stopping case, the process will proceed forever and until the computer runs out of resources. Right? What makes it very different is if we just flip back here. In this definition right here, there's no if-else. Right? There's nothing to differentiate when we want this to stop. And that's the issue that we run into when we're looking at this here. So it has no way of telling, hey, stop. It just says, do it. All right, and that's going to wrap this lesson up for today, folks. So until next time.